right? Expectation and variance. We'll start our session 15. So remember, like when we were talking about distribution, we talked about concept like expectation or mean or variance, which or like standard deviation, which is also a way to like talk about the distribution or the density of the function, like their qualities. And we'll be talking about very basic definition of these because you use them a lot in economics and also in math as well. Especially like we use expectation all the time, so it's very important you just know what it means basically. Okay, so expectation and variance, and why are we talking about this? Basically, well, I mean, if you do a lot of economic research, especially if you're making use of the data, you'll see that data makes up some distributions, all right? That is, if you like, I don't know, if you use R, data, whatever, and you have some data you're working with, and you plot the data, or any sort of data, as long as there are many of them, you're going to have some sort of like a distribution of data points, right? And for these data, they're making some sort of distribution as well. So, but the problem is because data has many points, and the distribution is very hard to like understand, because we don't know what to say about the distribution, right? So it's very nice if we could have some sort of parameters or some variables to kind of characterize these probability distribution. For example, what we would usually do is that, for example, think about a case where you have data for like maybe like all the wage for Korean people, okay? And then one of the natural thing you think about firstly is that try to find out the mean, right? Because like you kind of want to know because there's so many wage people has, you kind of want to see like what's like their average wage, right? And the second thing you might want to know is that you might want to know how the data is spread. For example, if you have the wage data and you can kind of see if the data is not that spread because like if the data are more close to each other, which means like many people in Korea are getting like similar wages, that would mean that. And if the data is more spread, that would mean actually Korean people are getting like different wages by people, right? That can also tell you a lot about the data. Kind of shows like overall like distribution. It can also tell you something about like the overall inequality or maybe some qualities about the data, right? Because if the wage is like spread very, if the data's variance is very big, that would mean like there's a lot of people who are really rich and really poor, right? Could give you some idea about maybe some inequality, right? For example, those kind of things. So one of the way when to try to characterize the probability distribution, like one of the thing about to find some pattern in the data is to first talk about expectation, which is mean or average, and variance, all right? So how much data, what's the mean of the data, and how spread is the data, okay? So what is expectation? So this might be easier because you might already know this. So if you have a random variable again, x, and we have the density function f, we usually define the expectation as follows. You might be more familiar with expectation. Even though we can do this in like a CDF term, I'm not going to do this for now. I'm just going to assume that we have a density function, okay, for simplicity. So the reason there's two ways to write this, I wrote it like here and there, is because the data can be, the random variables can be continuous or it can be discrete. So what does that mean is that, for example, there could be cases where the data is continuous, so it ranges from like some, for example, like 0 to 1. Those are the cases where you need integration to kind of see the probability, right? And their expectations. Otherwise, there's no point mass for the continuous data, right? Continuous variables. But unlike that, for discrete cases are the cases where basically like the data or the variables are discrete. So maybe there's like a point and top, like head or tail. We define this to be 1, define it to be 0. And 1, we get probably 1/2. And tail, we get half. Those are the cases where like the random variables are discrete. They're not continuous, okay? So in this case, what we do is instead of doing integration, we kind of just add up the values. So for 0, we times it by 1/2, we multiply it by half, and 1 multiplied by half, and we get the overall expectation of that variable, right? There's like 2 ways to write it. So that's expectation. All right. Okay. So, and because expectations are very important values, like we want to talk about some of their properties as well. So, what sort of property does the expectations have? And you might be more familiar with this, is that basically the expectation is linear. So what does it mean when you say it's linear? It's basically, it's this. So if we have some x, y random variable, and I put like this notation here, where x and y expectations are finite. The reason I did this is that we want to make sure that the expectations are like well defined. Because if it's infinite, it's kind of hard to define like the expectations, you know, when like adding them or like subtracting them. So it's kind of safe to assume that the expectations are finite, okay? And most of the time, it's not that problematic because a lot of our data are going to be not infinite in the expectation. So anyway, so we did that. And what A tells us is that EXY, so basically if we add two variables in the inside, it's same as just like adding them from the outside. So we have EXY cases, so, and then you can get it outside. So you can add the variables first and then do the expectation, or you can do expectation first and then add them, okay? That's how it works. And the second one is more easier to see, is that similarly, for cases where you have one random variable and you get an expectation of A plus B, it comes out like this. So you can kind of see that expectation for like constant is just going to be the itself. It's constant because B doesn't have like a probability, right? So intuitively, the expectation of B will also be B. That's why it comes out. And for A, it also comes out of the expectation. And you can write this just as this. So, intuitively, what you can think about is that basically what stays inside the E parenthesis are usually the variables that have some sort of probability, uncertainty. So A and B are like usually the values that doesn't have uncertainty, right? A are just A, and B are just, there's no like uncertainty attached to it. So in these cases, they can just pop out the expectation because they're not affecting the equation. Okay, there's no problem inside. But for x, because we have x is a case where there's a probability induced in it, we cannot take it outside the box. So x stays inside the expectations. Okay, so it happens. And well, I mean, this is kind of easy to see. So if x is bigger, their expectation is also going to hold. Okay. All right, moving on. And I want to talk about like the moment of random variable just for definition because you might see the term in econometrics or maybe microtheory. I'm not sure, but they're sometimes used and talked about. So I just wanted to talk about what that kind of mean because in order to show that you're not confused by it. So moment is very simple definition. So like basically you have a random variable x, and we just say the expectation of x to the power of k is the kth moment of x. So what we're kind of doing is that we have an x, and then we can like have a exponents where the value can range from like 1, 2, 3, 4, 5, and on and on. So when there's like a k value to the power, we say it's like exk is the kth moment of k. Okay. And it's kind of good to see that the first moment is always going to be mean, right? The first moment is just ex, right? So, and the first moment is about the mean, and the second moment, we'll talk about this, it's not itself a variance, but it's related to variance. Because if you want to define variance, usually you want to have it such that the ex, the second moment of x is finite to define the overall variance. Okay. And so if the second moment is finite, then the variance of x is defined to be as follows, which is in the bottom, which is we basically just do the square for x minus mu, and then we get the expectation. And just for notation, what mu is just, we call sometimes ex as mu, okay? So what that is doing is that basically, to write it more rigorously, what you're doing is you're just minus doing this, right? So you're just subtracting the expectation from the random variable, and then do a square, and then do expectations, all right? Okay, the variance. We talked about expectations, and now it's our time to talk about like what the variance are. And in an intuitive way to talk about variance, it just basically means how the data is spread. So if there's a bigger variance, that would mean the data is more spread. And if the variance is small, that would mean the data are more close to each other, all right? Okay, so how are we going to define variance? So we define the variance as follows. So what we have is that we denote variance of x to be VAR, just for your information. So variance of x is basically you have random variable x and you subtract the mean, okay? And then you square it to get expectations, all right? And you can kind of see that you can kind of enumerate this. What that means is that just square, right? We'll just do arithmetic, and you can get this, right? But if you minus x, you get. So what you're getting is this. And you're doing expectations. And we already know that the expectations are linear, right? So we can write this as like this. And then we can take this part out because it's linear, right? And it comes out because mu is not like it's just a value. It's not like a value that has some sort of probability. It's just like a fixed value. So it comes out. And this was mu by definition, right? Yes, it's mu. So that's why you get that. Right? So you start from here, you get this, and then you get ex squared minus mu squared. And from this, you can immediately see that the variance is going to be smaller or equal to the ex squared, right? Which is kind of the reason why we kind of said that it has to be finite, because we said that it's finite, right? Kind of, in a way, when you say you need to make sure that ex squared is finite, that kind of literally means that you're making variance be finite. So in a lot of the econometric classes, you'll see cases where when you define variance, you have a case where you say like a second moment and it's finite. And the reason you say second moment is finite is because you want to define a variance. So when you define the mean, you usually say like, there will be some assumption where you say like, the first moment is like finite. And then when you talk about the variance, there will be like some assumption that says like second moment is finite. And the reason they do that is this. They want to make sure that the variance is finite. All right. So the property of a variance, very similar, but a little bit different to expectation. Expectation had linearity conditions, right? So basically, like what is not a probability comes out of the expectations, right? Variance also has those similar qualities, but it's different. Like unlike that, basically intuitive way to understand this is that for variances, those objects that do not have like some sort of like a variance like quality, they just come out of the box. Like the constant will come out because like it doesn't have any like variance quality in there, right? So what I mean is that to be more specific, so for example, you want to get the variance of ax plus b, okay? So what has happened is that you just do what you have to do. You just do like use definition to calculate it, and what you get is going to be this. You can actually just solve it by just doing your arithmetic. I'm not going to go too deep about this. So if you do the arithmetic, what you do is that you have cases where a squared comes out of the box, and inside this part was the variance, right? So what happens is that if you look at here, adding something doesn't change the variance, at least like constant. So you could add something in the variable, it doesn't change it. You can kind of see why, because like, for example, like think about like a variance, like there's some sort of data with a variance. And what constant is kind of doing is that it's not changing the overall spread. It's just like shifting, right? By doing addition, you're just shifting the same distribution to the right. So that means the variance itself doesn't change, right? But like multiplying to a variance will change it. That's why a kind of stands, a is still here, and it comes out of the box by being squared. So a squared comes out, right? So that's why it's happening like that. All right. So adding some element doesn't change the variance at all, and multiplying some variables they come out of the variance, but you have to square them. All right. And using these concepts now, we can talk more about some of the different distributions you might see, and not very, but like very. Not easy, but some of the very useful distribution, and some you'll find it a lot, is Bernoulli distribution, where it's also like a discrete distribution. So you might want to consider making a probability distribution for a case where you have some sort of like a game where you can either win or lose, right? So in this case, is how you do it is that there's just like two outputs, right? You can either win or lose, like in a game, right? So if you win, there's a probability you're going to win by some percentage, right? And there are going to be some percentage you're going to lose, which is just like 1 minus percentage, right? You either win or lose. In this sort of games, you use like a Bernoulli distribution concept to define it. So basically what it has is that, oh, you say like x has like a Bernoulli distribution with a parameter p. If px1 is p, and px0 is 1. So we have like two cases. And you can kind of see like in an example, when the px is 1 would be like the case when you win. So when you're saying like x is 1, the probability is p, it kind of means that your probability of winning is going to be that p, right? P can be some element like 0.5, and your probability of winning will be half. And for p is 0, you get the rest of the probability, which is 1 minus p. So in a game, that would be like the probability of you losing, right? That's why you kind of say like a lot of the cases, like Bernoulli distribution, is related to like the cases where you win or lose concept of probability. So if you win, you're going to win by some probability p. If you lose, you're going to lose by some probability 1 minus p, right? So it's like a very famous discrete distribution in this case. So, and you can kind of think easily, for this case, you can kind of easily compute like the variance and the expectation, because there's just like 2 points, right? So how you do expectation is that you just sum up the answers for x is 1 and x is 0. So for expectation, I wrote it down. So it's like p times 1 times 1 minus p times 0. So why is that? It's because, remember like the discrete cases, expectation? We had this one in the number 2, right? So basically xi in this case would be either 0 or 1. And for 0 and 1, there is a corresponding probability, which is all half. I mean, not half, but p and 1 minus p, right? So you're just multiplying that and just adding them. And in this case, you get, so p times 1 and 1 minus p times 0. So you get p. So for Bernoulli, the expectation is always p, right? And for the variance, it's all simple too, because in the variance, you have to know about like x squared. But for the case of Bernoulli, you can kind of see x squared and x are the same, because x is either 0 or 1. So even if you square them, it's going to give you the same output, right? So because of that, we can kind of compute this more easily. So ex squared would be similar to expectation x, right? Which was p in our definition. So you because we have that, you can easily write this as just p, given it's ex squared. And remember the variance was this. I didn't exactly say why it's this, but remember like the variance definition. If you like solve it, what we can easily see is that actually the variance is the same as. You might have seen this already. So variance is same as expectation of x squared and minus the square of the expectation. Okay, that's another way to like define that variance. And you can see that we already know this is going to be ex, so it's going to be p, and this is also p, so p minus p squared. So p times 1 minus p. So interestingly, if you multiply your probability of winning p, which is, and your probability of losing, which is 1 minus p, you get the variance for the Bernoulli, which is why it's a very nice distribution. It's very easy to compute the mean and the overall variance, all right? That's why you use them. And I just wanted to point this out just before like ending the session. It's not really related too much about what we learned before, but this is just to talk about like the very brief about how we can just switch the integrals because you might not know them. So what this means is that very simple. Because this concept is like used in econometrics as if it's like so obvious, but it's not. So basically, you might later see when you take econometrics courses, one of the famous theorem you're going to first see is law of iterative expectation. So what that is, I mean, I didn't talk too much about conditional expectation, but just bear with me. So what you'll see later on is just like cases where you have a you don't need to know what this notation means. So just like writing these examples. So like what this means that just for like your information, I'm not going to talk about this, but there's this thing called conditional expectation. So like expectations are what we just did, right? We calculated like the expectation of random variables, but sometimes we can condition it. So we can condition something and calculate the expectation. Like the very nice example would be the case of wage. So think about the wage. What you can do with the wage is that firstly you can get the mean of the wage, right? So in this case, let's suppose that y is wage. And you can just calculate the mean of wage. Right? That's one way to do it. But sometimes you want to do some sort of like heterogeneity understanding of the wage. That is like you want to maybe know about what's the average wage going to be if you only think about male or maybe just about female, right? That's kind of similar as conditioning it, which is you're getting expectation of a wage conditioned to some gender. So what this means is that you're conditioning the fact that if someone is someone's gender is female, we will know their wage, or male, then their wage. Okay, these sort of are things where we kind of condition the expectations, and they're used frequently in econometrics and a lot of the economic researches because we want to in economics we want to think about a lot of cases where we want to think about the effect of some variable onto the output, and this like explained nicely into this concept of conditional expectation. We all know that, for example, we all know about if the male's wage or female's wage differ, right? And that happens when we know why it happens. And those concepts are like used and shaped using conditional expectation. And in those kind of concepts, a lot of iterative expectations are used a lot. Although I'm not going to explain what it is. You'll need to know about this, just an example. And those kind of concepts, when you use them, we implicitly assume the Bernoulli theorem, although we don't say we do. So that's why I'm just talking about this. In case you get confused by this. So what this basically means is very simple. So this term is important. If f is non-negative, or either f has a finite integrable value, which is here. So what it's saying is that as long as f is like integrable, that it can be integrated. As long as that holds in a finite number, what we can say is that if there are maybe two values, maybe the f is made up of x and y, you can switch the integration. So Because like there could be cases where you have a 2 value that makes up some sort of distribution or function, right? And you want to do some integration of it. And the most like the rigorous or abstract way to do it is that you do it by like both elements, right? D x y, like this. But then sometimes you want to think about, because I have value x and value y, is it okay if I just do it like separately? Like just do integration for x first, and then integration by y later on. And that's possible, okay? That's also possible. But then you might think about a case is, can I switch them? So you're going to get some value if I integrate y first and then x. And there's going to be also values if I integrate from x and then y, right? And you might think about, are they going to be the same, the value, right, in the end? Because it could be problematic if your values are not same. Because if it's not same, you can't do this. You're getting like different answers, right? And what Fubini theorem is basically saying is that as long as it's integrable, you can switch them. It's okay, okay? There's no problem by switching them. So if you have like doubt about whether you want to switch some x and y in integrations, that do come up very frequently, then you might wonder if it holds. But according to nice Fubini theorem, Fubini tells us that we can do it, so you can just switch it, okay? And that is also used in a lot of the concepts in econometry. Like what I said, like law of arbitrary expectation. You'll later see, like, in order to do this, and when you prove it, you have to like integrate by x and y, and switch the side. And that's possible because we assume this Fubini theorem. So I just wanted to point this out. Because there's a lot of cases where there are more than one variable you have to consider, and you have to take like expectations for both, and sometimes have like order for which to integrate first. And in those cases, these sort of problems will always pop out. In that case, just remember that it's okay, as long as it's integrable. So in order for this to hold, we must use Fubini theorem. That's why we're using it, okay? Just brief reminder. Okay, so this is the end of the session, and we'll stop here and take a lunch break, and after that we'll resume the class. So, and it might be possible that we end early today, so if that happens, we'll have some short Q&A time, and then we'll end the session, okay? 여기까지 할게요.